Welcome to the second session of this exponential and logarithmic function series. In this session, we will focus on the technique of applying the index laws to solve exponential equations and inequalities through 10 worked examples.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding, so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome to the second session of this exponential and logarithmic function series. In this session, we're going to focus on exponential equation and inequalities through 10 worked examples, and some of them are quite challenging. You may pause the video and try them out yourself at any time. Now, the first example has two exponential equations to solve, and both of them can be reduced to quadratic forms. So the techniques of solving quadratic equation can be employed here. As for the first question, we may assume a new variable to replace 3 to the x. However, if you are comfortable with the exponential form, you may keep the original expression as it is. As it can be seen that the equation of 3 times 3 raised to the 2x minus 26 times 3 raised to the x minus 9 equals 0 can be factorized using the cross product method. After factorizing the exponential equation, it is found that the 3 to the x equals negative 1/3 or 9. Since 3 to the x is always greater than 0, the only solution of 3 to the x is 9. Therefore, the solution for this equation is that x equals 2. Alternatively, you may transform to the logarithmic expression to obtain the solution. As for the second question, after combining them into one fraction and then set numerator equal to 0, here we may reduce the exponential equation to the quadratic form. After factorizing the expression on the left-hand side of the equation, it is just a complete square, e to the 2x minus 2, or in parentheses squared, equals 0. Therefore, e to the 2x equals 2, and hence x equals half times natural logarithm of 2. Example 2 shows an exponential equation of y squared equals a over x to the b. The question is to find the values of a and b given that the curve passes through 2 points, 1 over 2, 8, and 2, 1 over 4. According to the given criteria, we substitute the coordinates to the equation. So we have two simultaneous equations. A squared equals a over half to the b, 1 over 4 squared equals a over 2 to the b. After solving the simultaneous equations, we find a equals 2 and b equals 5. Example 3 is to solve an exponential equation 2 to the 3x multiplies 16 to the x plus 1 equals 32. Since the base 16 can be rewritten to 2 to the 4th, and 32 can be expressed as 2 to the 5th, hence the exponential equation becomes 2 to the 3x multiplies 2 to the 4 times open bracket x plus 1 close bracket equals 2 to the 5th. Since both sides have the same base of 2, their index on both sides must be equal. Therefore, after solving the linear equation of 3x plus 4 times x plus 1 in parentheses equals 5, we obtain the result 1/7. Example 4 is to prove an exponential inequality a to the a times b to the b is greater than or equal to a to the b times b to the a, given that both a and b are positive real numbers. The proof procedure is as follows. In case a is greater than b, since both a and b are real positive numbers, then a over b is greater than 1. Hence, a over b in parentheses to the a is greater than a over b in parentheses to the b. In case a is less than b, then a over b is greater than 0 but less than 1. Hence, a over b in parentheses to the a is less than a over b in parentheses to the b. In case a is equal to b, then a over b equals 1. Hence, a over b in parentheses to the a is equal to a over b in parentheses to the b. Therefore, we may conclude from the above that a over b in parentheses to the a is greater than or equal to a over b in parentheses to the b, which can be further simplified to a times b to the b is greater than or equal to a to the b times b to the a. Example 5 is a multiple choice question given that a is between 0 and 1, x equals a, y equals a to the a, and z equals a to the a to the a. The question is to make a comparison among x, y, and z. Since a is between 0 and 1, so a is less than a to the a, which is less than 1. Hence, a to the a is less than a to the a to the a, which is also less than 1. Therefore, x is less than y and y is less than z. So the correct answer is A. Example 6 is to solve 3 exponential equations for variable x. As for the first equation, since the exponential expression equals 1, and 1 can be written to 4 to the 0 power, hence the index of x squared minus 7x plus 12 equals 0. After factorizing and solving the quadratic equation, we obtain the x value, which equals 4 or 3. The second equation is the modulus x to the x squared minus 2x then equals 1, which can be rewritten to modulus x to the 0 power. So we equate the index on both sides of the equation and thus have the quadratic equation x squared minus 2x equals 0. After solving this equation, we have x equals 0 and 2. Since the base is modulus x, x is not allowed to be 0. Hence the answer is that x equals 2. As for the last equation, since 36 can be changed to 6 squared, so the equation becomes 6 to the square root of x squared minus 3x equals 6 squared. Since both sides of the equation have the same base, we equate the index and have the equation of square root of x squared minus 3x equals 2. After solving this equation, we obtain the result of x equals 4 or negative 1. The last step is to evaluate the obtained roots. Since x squared minus 3x is greater than or equal to 0, the value range of x is either greater than or equal to 3, or less than or equal to 0. And both answers of 3 and negative 1 are inside the implied domain, so the answer is x equals 4 or negative 1. Example 7 is to simplify two exponential expressions. As for the first one, we factorize both numerator and denominator by taking out the common factors of 2 times e to the negative x and 5 times e to the negative 5x respectively. After the common factors being taken out, what remains in the brackets of both numerator and denominator are just opposites in expression, which result in -1. So the simplified form of the first exponential expression is -2 times e to the x over 5. As for the second exponential expression, as it can be seen, after the factor e to the -2t being taken out from the terms in the numerator, the remaining terms can be factorized using the cross product method, which result in e to the 2t then minus 2, or in parentheses multiplies e to the 2t then plus 1, or in parentheses. However, after the factor e to the -2t being taken out from the terms in the denominator, the remaining terms are 2 minus e to the 2t, which is the opposite expression of a factor in the numerator. So the simplified form of the second exponential expression is -e to the 2t minus 1. Example 8 presents an exponential inequality, -1 less than 2 minus half times e to the 1 minus x over 2, which is less than 1. Here we separate the two inequalities and solve them separately. Then the obtained x value range from both inequalities are intersected so that it satisfies both inequalities. Hence, we find that the x value range is between 1 minus 2 times natural logarithm of 6 and 1 minus 2 times natural logarithm of 2, not including both endpoints. The exponential function fx in example 9 equals 2 to the modulus of x plus 1 minus modulus of x minus 1. The question is to find the x value range given that fx is greater than or equal to 2 square root 2. Since the exponent of function fx is expressed in modulus form, we need to discuss different value range of x so that we can remove the modulus sign and hence find the x value range accordingly. So when x is less than -1, fx can be expressed to 2 to the negative open bracket x plus 1 close bracket plus x minus 1, which equals 2 to the -2, which is less than 2 square root 2. Therefore, when x is less than -1, fx equals 1 over 4, which does not satisfy the requirement. Now, when x is greater than or equal to -1, but less than 1, fx equals 2 to the 2x. By solving the inequality, the range of x is obtained, which is greater than or equal to 3 over 4. After intersecting the obtained range with the assumed range, we obtained that x is greater than or equal to 3 over 4 but less than 1. Finally, when x is greater than or equal to 1, fx equals 4, which is greater than 2 square root 2. Therefore, when x is greater than or equal to 1, fx is always greater than 2 square root 2. Hence, in summary, the value range of x is the result of the union of the set that x is greater than or equal to 3 over 4 but less than 1, with the set that x is greater than or equal to 1. Finally, when
x is greater than or equal to 3 over 4, fx is greater than or equal to 2 square root 2. There is a function fx in example 10, and it satisfies the equation 1 plus fx over 1 minus fx equals 4 to the x. If x sub 1 and x sub 1 are two positive real numbers, and they satisfy the equation of fx sub 1 plus fx sub 2 equals 1. The question is to find the minimum value of f of x sub 1 plus x sub 2. According to the given equation, 1 plus x over 1 minus x equals 4 to the x. This expression can be transformed to x equals 4 to the x minus 1 over 4 to the x plus 1. Since f x sub 1 plus f x sub 2 equals 1, then we can substitute f x sub 1 and f x sub 2 into it, and then simplify the equation to 4 to the sum of x sub 1 and x sub 2, which equals 4 to the x sub 1 plus 4 to the x sub 2 plus 3. After further doing the algebra manipulation, we can express 4 to the x sub 2 equals 4 to the x sub 1 plus 3 over 4 to the x sub 1 minus 1, as it can be seen on the screen. On the other hand, as for f of x sub 1 plus x sub 2, we may substitute x sub 1 plus x sub 2 into the fx, and it equals the quotient of the result of 4 to the x sub 1 multiplies 4 to the x sub 2 minus 1 to the result of 4 to the x sub 1 multiplies 4 to the x sub 2 plus 1. Here we continue work on example 10. As it can be seen, the expression of f of x sub 1 plus x sub 2 after being simplified becomes 1 minus 2 over the sum of 4 to the x sub 1 multiplies 4 to the x sub 2 and 1. Here, in order to simplify the algebra manipulation procedure, we assume a equals 4 to the x sub 1. Hence, 4 to the x sub 2 can be expressed to the quotient of a plus 3 to a minus 3. Based on this assumption, f of x sub 1 plus x sub 2 can be expressed in terms of a, which equals 1 minus 2 over the total of a times the fraction of a plus 3 over a minus 1, then plus 1. The expression can be further simplified to 1 minus 2 over the total of a minus 1 plus 4 over a minus 1, then plus 6. Since a minus 1 plus 4 over a minus 1 is greater than or equal to 4, f of x sub 1 plus x sub 2 can be simplified, and it is greater than or equal to 4 over 5. Hence, the minimum value of f of x sub 1 plus x sub 2 equals 4 over 5. Here we provide a summary on example 10. Based on the relation between x sub 1 and x sub 2, it is worth to note that the algebra technique of transforming the expression of f of x sub 1 plus x sub 2 to a proper fraction containing 4 to the x sub 1 only in the denominator is quite powerful, which enables us to apply the basic inequality formula to obtain the minimum value, and at the same time cancel out the both variables x sub 1 and x sub 2. In the meantime, the assumption of 4 to the x sub 1 equals a makes the algebra manipulation easy
to read. The technique we demonstrated transforms the expression from improper fraction to proper fraction and reduces the expression from two variables to a single variable. Finally, it is worth to remember that the form of y equals ax plus b over x, in which the minimum value is independent of x value when x is greater than 0.
If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.